Okay, guys, so today we're going to continue our discussion of trigonometry, okay? You guys remember, we've worked with this already. What is this called?
Circle.
Not just a circle.
Unit circle.
A unit circle, right? It's got a radius of 1. It's married with a geometry married with coordinate plane, right? So we're on an XY graph. Before we begin, okay? Today we're going to be talking about trigonometric functions, okay? Specifically, today we're going to focus on sine and cosine. Now, I know a lot of times when we talk about math, we talk about really heavy theoretical stuff, but this has actual application in reality, okay? Specifically in something I know you guys all love, noise, sound, even music, okay? What sound is? Sound is a compression wave. It is a form of energy. And a compression wave, when it's in a medium like air or water, it produces vibration. And the vibration, when connected with something smart like your highly intelligent brains, can sense hearing. Pretty cool. But not only is it just something that you sense, it's not only a sense like music or noise, it also can vibrate material in real life. So here's a really cool video I want to show you guys of how sine waves affect reality. You guys see this setup right here? You see this machine's got, it's a speaker, okay, with a rubber hose. There's a water source, a tone generating thing, right? And it's got 24 hertz, which is it's a unit of measurement of frequency, which we're going to talk about next lesson. You guys see what's going on here? Pretty cool, right? So not only is this, I know this looks like magic, right? But there's a couple things going on here, right? First of all, there is the compression wave, the 24 hertz sine wave, that's being pumped through the speaker into the rubber hose. But it's not just making this shape. You have to understand also that the camera shooting this video also has a frequency rate known as a refresh rate. How many frames per second are they shooting? So it looks like a still image. But really what's going on is it's partly a video effect, partly a cool thing which sound and sine waves does. Pretty cool. You see that? That's changing frequencies. Pretty magical, right? Right on, guys. Okay. Wonderful. Okay, so I want to do a quick review of a couple things. Okay, so first of all, unit circle. We have our x, we have our y. Where's our third? What's our third variable, first of all? What's our third variable? Do you remember? Some on theta. It's a theta. And theta is a measurement of what? Is it a measurement of vertical or horizontal position?
Away from the x-axis.
Away from the x-axis. How so? This way? This way? This way. Everybody remember, get up, and we're going to do the exercise, right? Excellent. Okay. So theta starts at 0 right here, right? And as it increases, okay, in radians, remember we're dealing in radians. It goes like this. It goes up, 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 1 radian, 2 radians, 3 radians, 3.14, aka pi radians, right? And then we do another one here, all the way back down around 2. This would be 2 pi, right? And what if theta were to go negative? Which direction would it go if theta was going negative? Theta would go in the opposite direction. Very good, everybody. Right on. Okay, great. So we reviewed that. Here we are. I want us to understand that in this mini unit circle, right, we have this definition of theta as going rotationally around, right? But theta doesn't need to be a rotation. Theta can also be like x or y, which are rectangular, right? They are rectangular, that means that if x increases, we go in a position, in a direction, one way, this way, right? And if y increases, we go up, y increases, we go down. So theta can also be described in this notation. So I want us to, again, please look at the screen. I'm about to show you a very cool graphic, okay? We have the marriage of geometry with the coordinate plane. So it intersects at points along the circumference. And all those intersections have special identifiers, which are your x, y coordinate pairs, right? So let's examine how do those x and y coordinate pairs change as theta increases around the circle. If we watch here, I want us to first take a look at this top one, cosine, okay? What's going on is as the angle changes, there's a vertical, see this blue line here? It's going 1 to 0, down to the negative 1, back to 0, back to positive 1, okay? And how this translates here is as theta increases, it's our x-axis, okay? Our y-axis is going to be our cosine function. So here, the x-coordinate as theta rotates around the circle, our x-coordinate is our cosine value, okay? So as theta increases, it hits 0 to negative 1, bounces back up to 0, up to 1, back down to 0, and this is periodic, so it's going to continue as a wave. Alright? Now if we look at sine, it's the same idea, except we're not looking at the x position of our intersecting point of the circumference. We're looking now at the y position. You see this red line? It's going negative 1, 0, positive 1, back down to 0. Does everyone see that? Okay, and so, if you guys took out your unit circle diagrams, which I'm sure you all completed for homework, you would see that a table graph would indicate the same thing. As long as theta is our input value, typically where we would see x, our output value would be y. Now we replace our input value with theta, okay? And whether or not it's x or y depends on whether or not we use cosine or sine, okay? And so, when you have x and y, and this is your sine or your cosine graph, okay? Pi, 1, negative 1, this is 0. It's going to look something like this, okay? That would be cosine x equals cosine x. Here I'm using x and not theta because, as you see, I defined my axes as x and y. So it's important to do. Remember to label our axes. If I do sine x, I'm going to use a different color here. Okay? If I use sine x, it's going to look a little bit different, but they're going to be related. We're going to talk about that in later lessons. Okay? But same idea here. We have a pi, which would be 180 degrees. 360 is 2 pi. Okay? They're going to look similar. They're not quite the same, though. And we're going to talk about that as we move forward. But here is your first assignment to work together in partners. So, Jordan, if you don't mind, please moving over to this table. I want you to do this assignment, okay? Here is y equals sine x, okay? I want you to write a formula with this new function that you have. I want you to tell me, how could I move this in such a way where I want sine x moved up 2 units. 2 units, okay? Oops, sorry. Units. With you guys, I want you guys to tell me, what would cosine look like? What would the formula, the equation look like if it was moved 3 pi units to the left? Okay? Go ahead and split up for seat work, begin, talk amongst each other, try to figure it out. I'll be around to help you guys. Now, question for you.
over pop. That's what I'm
That's
thinking.
a really far ahead point. It's a periodic function, so it would phase into SLS, so into pop. So think about cosine x equals 3. We can see the term as cosine
But how would we express that mathematically? That's another thing. So would it be
So I'm just going to share what George and Lori have already figured out. Maybe this will be helpful. Now, if you guys remember, we talked about this much earlier in the year. Okay, there's certain types of manipulations we can do to parent functions, right? I'm introducing two parent functions today. The same rules apply. Okay, remember we've talked about this before. That there's three ways to manipulate a graph. Okay, there's shift, there's shape, and there's flip. Now, based off these three, which of these three are we talking about in these two? We're talking about shift. Sorry, I didn't even throw the answer. I'll let you guys decide first. But shift here, right? When we're doing shift, all we're doing is we're taking the function and we're just moving it positionally. We're not changing the shape, and therefore, because it's shift, you guys remember which operations are associated with shift? Plus and minus. Which ones are associated with shape? I'm sorry? Multiply and its sister divide. And then flip, just to finish it off, this is some usage of negatives. Okay? Now, do you remember we talked about this only in a little bit of detail, okay? But when, for example, in vertex form, when we shift vertically, so I'm just taking the function and I'm positioning it from its original parent function position, I'm just moving it up or down. Is this plus minus, is this inside the function or outside the function?
outside?
Outside the function. So here's sine of x. If I were to write it in function notation, I would say it's f of x plus 2 on the outside here. So if vertical position shift is on the outside of the function, how would we do this? Left here is a horizontal vector. So how would we describe that in function notation? Inside, but let's orient it for this equation. So what am I? How many units am I asking to move to left?
F of x minus.
So we're moving to the left, right? We're moving this to the left.
Oh wait, it's counting two, so it would be plus.
It would be plus. You have a point, and in this instance, because it's a periodic function, it doesn't matter. But I want us to be consistent, right? So you're very right.